Hello, welcome back to the stream. I'm Jun Chan, and we're back doing some Purescript and some graphs with the algebraic graph a library that we're porting from Haskell, and we're implementing a Comonad instance for it. And we've been last time basically piggybacking on the good idea from my friend Paolo, who pointed out that pun not intended, that maybe our pointed graph instance or data type should look something like this. And until now, I was more looking at something I've been calling, focus graph is fine, but context graph. This idea of sort of extracting a context in the way that it's done. Well, to be honest, in the way that it's done in this blog post that we've been looking at. But this blog post that we've been looking at is actually based on the Haskell FGL library, the sort of the original attempt to do graph structure in a more functional style, which is from a while back actually. When is it from? 2008. Yes, it is from a while back. And but we're doing algebraic graphs, and that's another way to do graphs. And it turns out that it's not, I don't think, very well fitted to do a more context-oriented approach. Context being this idea of focusing not just on the vertex, but focusing on the vertex and its edges. Well, I mean, there's a bunch of things that allow to convert an algebraic graph into a sort of a more context shape. I think it's in internal. There's this focus aspect. And then I think in the original graph library, there's also something called context, actually. And context, indeed, takes a predicate and a graph and returns a maybe context. And that's fine, but let's say that I think there's several aspects to this. One is, well, it uses this focus aspect, so it needs to fold over the whole graph. And then it needs to match a predicate and then output these inputs and outputs that also the edges, incoming edges for directed graph, incoming and outgoing edges, focused on the, well, in this case, it's actually a sort of an aggregate, I suppose, because this A to Boolean could focus on several nodes, actually. So I'm not sure exactly how that would work. I think it's accumulating. Yeah, the fold G is actually using I think a monoid instance on this overlay foci and connect foci. So on the focus data point, so or data type. So if we look into internal, I think we have the focus data type, and then everything is a list. So when we do the fold G, we use the monoid instance, I believe, and we use connect foci and overlay foci to append right here the inputs and the outputs, which are lists. So it's just concatenating the lists. So in the end, we get all of the inputs and outputs edges for a given predicate. And I think the idea is to locate a subgraph and then be able to kind of connect, I suppose, the subgraph to the external graph. And that's the similar thing as a context, the context being only focused on a single point, a single node or vertex. So that's all good, but I think there's several things, right? Like one is well, we use the fold G, that's fine, but it's a walk through the whole graph. It's a traversal of the whole graph. So all that to extract just one context seems that it's a bit well, it's computationally expensive, and well, the thing is that this context matters in the FGL library, because that's the kind of the inductive unit. When you start to, for instance, pattern match on a graph, that's what you get. You're actually pattern matching successively onto context, and basically extracting a context until you get nothing, which is a little bit like sort of thinking of the graph as just as a const list, right? As a linked list, where and that is part of the premise. Is can we do? It's really super easy to program with lists in Haskell. Like pattern matching with lists is really super pleasant. How do we do the same thing with graph? And FGL addresses that by saying, well, actually, we can pattern match on a context and the rest of the graph, and then continue doing that until we've consumed the whole graph. But the thing is that algebraic graphs are an attempt to do that, but from a different viewpoint, from this construction that is vertex and overlays and connect as the sort of the algebra to build your graphs. So it means that really pattern matching is not going to be pattern matching in the way that FGL does it, even though that's very elegant and again, the source of how graph decomposition occurs in the blog is described in the blog post. But here, when we're doing the equivalent, instead of matching on a context and then having the rest of the graph, here what we're doing is actually we're matching onto that graph representation, and then we're finding these constructors. We might be matching on the graph, and then we have an overlay constructor at the top, gives us two graphs. We continue pattern matching on that, and we might find a connect, and we might find a vertex, we might find an empty if we have a graph that allow an empty nodes, and that's pretty much it. That's the way that this graph decomposition would work, or the pattern matching on graphs would work. So it kind of makes sense to actually go along the grain, right, rather than across the grain here, because and that's what I think is genius in what Paolo suggested, which is this pointed graph, which is going to use these different constructors, but is going to make sure that we're always pointing to some part of the graph that is, let's say in this case, arbitrarily on the left of our constructors, and then appending like a normal graph on the other side, such that we, even if we're at the top, we always know how to traverse our structure to point at the vertex that is the one that we want to point at. And then all the other ones are just going to be regular graphs which don't have that pointer. So it means that it should be fairly easy actually to at least do extract and for a Comonad instance, and I think that's kind of where we were. We were about to do extend and extract, so that's what we're going to play with now. But I do want to say something about this. I think yes, what we done last is that we tried to make sense of how to actually construct one of these pointed graphs, and in this case. We have one of those here, and I just realized that we have two p vertexes here. Yes, right, because this is a pointed graph of pointed graphs that we built. It's not a pointed graph, and we need to build a pointed graph of pointed graphs if we want to extend properly or duplicate. And so I was a little bit lost trying to understand how I needed to build one of those, but here this is clear. What's in the vertex constructor on the right hand side of a connect here is another pointed graph, and that's what we have here. We could just have a p vertex, right? But we have a whole pointed graph in there, and we just happen to have the same pointed graph in the other side. So that's what an actual pointed graph would be, because I was sort of a little bit struggling. I had basically I just realized what I was struggling with, and I think it can be seen here. So I was trying to build a p-connect of p-connect, but really I needed to make sure that in the leaves of my pointed graph is where I have another pointed graph, whereas by stacking p-connects, I was just continuing to build an actual pointed graph without a pointed graph inside. To put a pointed graph inside, I need to put it in the vertex in the leaves of the data structure, and then inside that put a pointed graph, which is done right here. So with that insight straightened up, we can now probably build extend and Comonad instances for it. But I wanted to reflect a bit on something that I haven't been discussing too much or thinking about too much, which is that in the Arga talk, Andrei Mokov specifies that there is a way to build like a canonical form for algebraic graphs. And I don't know if that's going to matter. I'm now just thinking about this idea of graph rotation and how well that's going to work out with this particular representation. And it's going to be interesting to try and actually, represent this graph. And I think we've done that, but then try and rotate it and understand how rotation works. So rotation, as long as we're not keeping the contexts, which we're not, so contrary to here, it should mean that we're just rotating on the focus, and that should be fairly easy. But I want to know with an FGL, and maybe we'll have to go back to Purescript FGL, to be honest. I like algebraic graph. The more that I think about it, the more I'm thinking that FGL is actually a pretty good representation for how I'm thinking about a graph. And it might also maybe relate to then further exploration that I haven't even talked about yet either, which is this idea of, how hypergraphs and a particular type of hypergraphs can be used to represent dynamic systems. And that points to work from Evan Patterson, David Spivak, currently people who are working at the Topos Institute, and looking at how you model dynamic systems and how you compose dynamic systems. And this idea that you can do that with this decorated cospan idea, which is basically the way that my intuition is built around this is maybe an extension of this idea of a context. It's basically in this case, it's an open graph. So I think in that case, it's not called a graph anymore. It's a graph with ports. And then the decorated cospan is a way to link the ports to a holding structure, determining whether those ports are show out the composite structure or are connected to something else inside the structure. So there might be a generalization of these structures, but anyway, I don't know if we're going to even get there, but I keep that in mind because I want to be able to represent things that are as complex as dynamical systems. It's interesting to think about what a comonad means. Well, I think a comonad is just a cursor. It's just a convenience. Like if you have a text file, then a cursor is super useful to have or arrange because you can then move things around and decide where to go. So I think as a maybe like the concept of a zipper, right? Having a pointer or focus or a way to point to a thing inside the dynamical system is super useful. And so popping back the stack here, I'm thinking FGL might actually maybe be more convenient for that because there's some arbitrariness into this algebraic structure. The fact that you can have several like same graphs represented in different ways, even despite the fact that you have this canonical form or normal form. I think it might be better to use FGL, but I'm not 100% sure. One of the reasons why we might want to continue here is, for instance, the labeled graph, because labeled graph has this super compact representation here with just the vertex and that connect annotated by an E. And the fact that this is so compact, I think might mean that we can I don't know, to be honest. Maybe it's going to be easier to use somehow. I suppose that's my intuition, but I mean, as I say this or think this, a counter voice comes in and say, yeah, but you still have the same problems with, like, even if you have a choice of type of edge that, you know, represents just your overlays and your connects, you still end up with the fact that you have multiple possible similar representations, that you therefore might need to convert to some normal form in some cases, at least for instance, to just even do equality, right? And that might be computationally expensive, and then that things like rotation might also not be completely, might not fit that model very well, whereas it seems like a context-based data structure, maybe that will make things simpler. But then again, I think maybe, like now I'm thinking, but won't FGL have the same problem? Doesn't FGL also has several representation for the same graph? And that would be an interesting thing to think about. Let's look at data graph inductive. Okay, so maybe data graph inductive graph static. It does have graph inspection, graph type class, fold projection, subgraph inspection, context of a given node, a label for a node, neighbors, petit printing, ordering. And graphs can be used as map keys. Yeah, that's graph as map keys is a interesting mind-bending concept. It might be in the paper there where we'll be able to find something related to canonical representations. Anyway, we're finishing here with Aga, or doing more work with Aga, and but I'm thinking maybe we'll go back to FGL at some point. Okay, so let's go for it. We have now some idea of what a pointed graph, so a duplicate might look like. So how is that going to work? If we encounter a p-connect, then I suppose we need to again, yeah, what do we need to do? It's not clear. Yeah, these type annotations aren't needed. Okay, let's think about it in the simple case. Let's say we have a p-connect of p vertex true and vertex false, for instance. Duplicating this would mean what? It would mean that we put the p-connect inside the p-vertex. We put the whole thing inside it. And then in vertex here, in the other branch, we put this time the two-graph version of that, which is connect blah blah blah. No, it's not. We put the same thing. We put the same graph in there. So it means that we need to keep track of the top level graph that we're extending. So basically it means that we're putting PG inside the vertex. We're not inside P vertex, we're putting FG, I mean, not PG. That's what we put inside the vertex here. And then when we p-connect, what do we put? Nothing. We just do PQ. It's the same thing. It's only at the leaf that it's going to change. And Okay, yes, I think because I can't have type here. And then I need to make sure that that this extend is correct. And to do that, I think I need to go into package Comonad and just check that what my law is supposed to be. Extend f is fmap f duplicate. So yeah, fmap so it is this. So it's not right. Trying to match pointy graph A0 with type pointy graph. Okay, what's going on here? Given given duplicate, why would p vertex of fg not work? Yeah, I don't understand. So here we have a A0, A1 problem. Pointed graph only has one type. What am I missing here? P vertex FG has type pointy graph, A0, but it finds its pointy graph of A1, and here it looks like I have here I have one wrapping of pointed graph missing, which so you're trying to check that FG has pointed graph A0, but then you find that it only has type pointed graph A0, and I think it's because it's duplicate here. Otherwise, how am I going to get to the yeah, but this am I going to leave the other leaves intact here? I'm not, right? The other vertices. The one that are here. That means that you want the graph Comonad, right? And you'd be using the duplicate from the graph comonad. But that's correct though, right? Because I do want, in vertex, I do want to put this in. And here I can't do this if I'm not drilling down on the graph instance as well. So here, duplicate, it would be basically graph.duplicate. If I import algebra graph as graph. Or not, because it's the Comonad instance. Let's duplicate from Comonad. So, okay, so does this mean import control Comonad, duplicate as Comonad? I want an error message that tells me that I don't have a duplicate instance for Q, or Comonad instance for Q. Here, however, when you're checking pconnect duplicate P and duplicate Q, okay, you know what? I think that's maybe what I should do is, since this is local and what we're really describing here is extend, we can call it dupe, and then we say that this is dupe, but this is duplicate. Should avoid being confused about names, but you get the same error. So you're saying so you're checking the pconnect dupe. Oh, okay. Hold on. What? Pconnect duplicate Q. As type T0. Here I'm duping FG. Yeah, there is a problem, which is that if I'm expecting that this duplicate is going to contain my original FG in it, then I can't just duplicate. I actually need to extend const FG. And you don't find an extend for graph. Okay. I wonder what duplicates you were getting now. But okay, so I thought I had done the beginning of a, no, I had not. Okay, but I feel like I'm armed now to do one. I feel like I know how to go along the grain. So let's try it. Oh, what am I saying? We have a problem, of course, about non-emptiness here. So actually, we want the non-empty version. And yeah, in Nonempty we don't have yet the Comonad instance, but that we can have. Yes, okay. Good, good, good. So vertex connect overlay here, and vertex connect overlay. We can, right? What is it though? No, that's going to be a little bit arbitrary. No, we can't extract. But can we extend and not extract? Ooh, fancy. I think that might be the case. Because if we can extend, then we don't need to have any special node that's pointed to, but we can refactor the graph by putting something else in each leaf. That's totally possible. And so what does that look like then? Extending, so we'll do BFG, and so we would put the vertex there, and then we would just do the same here. Is that just what it is? That doesn't compile. Why? A non-type focus graph. Yes, that makes total sense. In fact, I don't think we have a context underscore here anymore. Oh, maybe we do. Yeah, it type checks. And so do we have now an extend that we can use? We do. And then we just have something we're not using here. But apart from that, do we have a Comonad instance then? I mean, we have an extend, and we have a Comonad, and we don't have type errors, or do we? What is this? Enable to pass module pointed graph. Okay, so no, we're not done. What's going on? No, that's fine. Okay, let's confirm. Let's Spago test. And then I suppose the next thing is to cannot import focus graph from graph nonempty in class. Okay, that's all good. What did you do with focus graph in the end? I think we put them in pointed graph. Yes, we did. So let's go to class, and I think it will be in pointed here. I suppose it could be just pointed, right? It completely could. Non-empty and pointed. Yeah, let's do that. And will it be pointed graph? I mean, yes, that's pointed graph. And then do the test work. Same import problem. And okay, save. Here we go. You are now import algebra graph non-empty pointed, and context prime is also there, I think, as well as the lowercase version, right? Indeed. And we focus. I think we left in. Oh, where did we? Oh, maybe it is also in pointed graph. Yes. And so here, Jabi. Okay. And context prime we don't have anymore. We actually, yeah, I think, yeah, because I called it context, but we're also not using it anymore. So am I actually using that data type in my tests? Prime? No, I'm not. Okay. I think this is now called context. Actually, maybe I'm not using that anymore. No, I'm supposed to. Okay. And that's, yes. Okay, so I am trying to do context on nonempty graphs. So maybe I need to, but yeah, but this is context. So I suppose it's just a different context than from here, right? Yeah. So let's qualify those and any graph. That's good. We have what we need. We can do any graph dot context. And here. However, the type seems wrong because here I think context prime was an innovation. Let's see. Maybe it's now context. Yeah, context underscore maybe. Yeah, it takes the graph and yeah, I think that's the one I'm looking for. So test and context underscore. Although to be honest, that looks exactly the same. No, right, okay. So the context underscore, there is one that it outputs that doesn't output the vertex, and it doesn't output the vertex. So yeah, so I think this is part of me trying to make context graphs, but I think yeah, I'm not so sure anymore that I want to create this particular interface. So then what do we do with these tests? We just I think we just remove them. And we say not so sure about context graph anymore. They work with FGL, but here maybe not so well. Okay, and okay, so we can test maybe. Yes, we can, and we pass the test. So let's now write some proper tests for well, we want to test extend actually for regular graphs, not the pointed ones, and we want to deal with that warning here, and maybe deal with all the warnings. How about that? Axis was shadowed. Okay, wise and wise. And imports, and GG was shadowed. Yes, because I have this here, which probably would help us in tests. And yeah, we'll apply our suggestions here and have more suggestions. Pointed yeah, no, algebra graph into the pointed. That should work. Yeah, it does work. And okay, this needs to be reloaded. It's weird, this treatment of files that were open once and had warnings, but don't have anymore. And yeah, just maybe build. How about that? Okay, that makes sense. Yes, you don't know what nonempty graphs are, and that makes sense because I haven't imported them. Okay. And we don't have the constructor for vertex. Interesting that we haven't imported that. So we imported graph without its constructors. Okay. That's fine. We can just say vertex. And here as well. And that's interesting. Yeah, because that's the non-empty vertex, in fact. Does it need to be? Non-empty, non-empty. It doesn't. It can be the regular graph. Which means we can also create an extent for the regular graph, which also totally makes sense that we can. Okay, that's interesting stuff. Here. And this should just work. No. Yeah, well, empty is just empty, and that's fine. Indeed it is. And indeed we don't use the whole Comonad, but only extend. And then in this case, well, so now we're saying this is not going to be non-empty graph. And so but when we convert, we kind of want to go to non-empty. I mean, we could do both, actually. And this one is this one. And I suppose we can write it like that. I mean, to be honest, this is going to be replaced by our classy versions. But for now, let's try. Let's see. We don't have focus in our graph. That is weird. Yeah, I thought so too. It's a little bit weird that we don't have it here, but yeah, I thought so too, so it should be exported. Okay, and here we want any.vertex, connect any.overlay, and to any graph. Yes, except, well, interesting. Interesting indeed. This is actually going to be two graph here, isn't it? So now we've changed, right? Now our right-hand side is a regular graph. It's not a non-empty graph. And when we do to any graph, to non-empty graph, then convert that connect. It should be a non-empty graph here. And now we need to convert a regular graph to a non-empty graph, and we can't do that. Okay, so maybe it's not exactly that we can't do it, actually. That's interesting. We can, but we need to do a little bit more work, because we have a p vertex, and so we know it's not empty, the result. But then on this side, we could have emptiness, but that shouldn't be a problem. So this needs more work and more thought. And maybe we can do that when we do the classy version. This should work, but needs more thought. And so the two graphs though is simple, and then immediately we're using the new extend from graph that we just added, and then what? And then here we don't need to use any vertex anymore. We use just vertex, and now it type checks, and in this case we don't need non-empty anymore. But when we're trying to do focus graph, right, so focus graph now has changed type if I don't use any graph in it. And so let's look at our focus graph again. Should this graph be non-empty? Yes, in this case it should. So let's get back on non-empty here, and then let's make sure that our focus graph has any dot graph. And anywhere else? No. And then therefore, maybe here. We refocus. Maybe. How does this work? Any dot focus. And we don't need that focus for now. And we can remove the constructors. And this now works. And our test. Pass again. All right, so let's now do some tests for our pointed graph. Oh, I said that I would test extend for just regular graphs. It extends, so we can do the law. It extends const identity to the same graph. That's I think that's the law, right? Extend const identity. And then let's take, well, we have graphs, I think, up there. For instance, yeah, for instance, that's an adjacency list. Yeah, this thing is a graph. We're just going to need to do adjacency list of that, and we can take the should equal. We're just taking a fairly complex one just to check. Okay, so we want adjacency list of extend of this circuit, and indeed that should equal exactly that same thing. And we just need to import Comonad. control Comonad. There's some, yeah, there's some trouble in the parentheses here. Let's need another set. Isn't that right? So it seems like it needs a type annotation now, because extend doesn't help find the right type. Very interesting. Yeah, I think if I say a graph of char, I should be fine. Except I need to do it maybe here. Or let's do it here. Put some parents here. No? No, hold on, what am I saying? Yes, adjacency list. So you don't know what the type of the adjacency list is. A list of tuple of A. Oh. Is it const identity or is it just identity? Tuple of graph of char. Right. Ah, yes, yes. No, okay, so const, let's say const A, and now we have everything with A's inside. Which means we collapsed the graph, by the way. So does this mean, I mean, it type checks, but does it pass the test? It does. So by doing this, we collapsed the whole graph to having a single node A. And that's fine by me. What else could we do? So that's not that const A to the one node self edge graph. So what am I thinking then? Yeah, clearly const identity is wrong. What the law that I'm thinking of is extract, of course, but we don't have extract. So what other law do we have? Well, let's take a look at reading Comonad here. So extend extract is ID. And that's extract. Yeah, no, that's what we have. I could get like the size or something. I could do size. I could do anything that has, yeah, like size, or has vertex or whatever, edge count. So I think size is good. So let's do size. And so extend size should give me a graph with a single node. Okay, maybe there's something more interesting to do here. Vertex count, edge count, vertex list. There is simplify. Where is simplify? Aha, I think that's the canonical, that's the thing that brings it to normal form. Oh no, it does not compute the simplest possible expression. Let's do size and just see. This has 1, 2, 3, 4, 5, 6, 7 vertices, I believe. So I think this should just be on this graph. And we need to import size from graph. Okay, and we test. And 12, okay, so that includes the vertices, I believe. And so that's fine with me. 12 is a good number. I mean, we could do like a simpler thing, like let's do vertex unit and make sure it's 1. Yeah, no edges. Wonderful. Okay, so this is all good. We could do the same for non-empty graph. Let's do it. And do we have a non-empty circuit? I think we do. So let's just do non-empty overlay, non-empty path. From array, I don't think I should need to. And then I need that for vertex though. And some weirdness. Oh, what? Any graph, I see. Yes, list with non-empty list. I think I have a... I should have a from array for non-empty list. How does this work? Right. I forget how this works. Non-empty. Internal from array. Non-empty list. Yeah, let's just search engine pursuit. Non-empty. from nonempty, I should be able to get to use foldable or unfoldable. And it's probably unfoldable. And no, it's not. Yeah, I don't get the I don't have a from array instance for non-empty lists. Did I really not build one? Have two unfoldable. Yeah. No. It's just a lot of back and forth, but I think it will work. Yeah, I need to import it. It's in internal. And I need the any graph version of adjacency list. And the any graph version of adjacency list here. Don't know what the deal is here. Oh, I might need any size, any graph size. Yes. And you don't have unfoldable for an empty list. Oh, unfoldable 1. Oh boy, so not that. Not that. So, okay, let's think about it differently. Any graph circuit takes a non-empty list. So I could just do this. I think. And yes, I can. Very good. And we can run the test. And it passes. Okay. And so now we also have a Comonad for pointed graph. And so we could do the extend things, but the more important thing is to do just to extract. I mean, actually, we can do the Comonad laws. Extract, extend extract equals ID. So extend extract of, let's say, this complicated thing is going to be the same complicated thing, which we need to grab from right here. And now it's not any graph because it's pointed graph and pointed. Okay, so how are we extracting to be fine? It's just that we need well, yeah, we have none of the methods implemented, so we'll need to implement methods. So here, I'm going to move this whole thing into an empty module called context. We don't know whether it's going to be used or not. Can always name the module. And leave the commented out stuff in there. And then we do circuit and other things. We probably need to implement them all. That's where I start to continue eyeing at class here, but for now, let's check out circuit here. Maybe we take it from do we take it from Nonempty Graphs? Oh wow, it's so much simpler for Nonempty Graph. Crazy. So can we do it with Nonempty Graph? Well, so part of it is that we start from a non-empty list, and yeah, I mean, okay, well, first of all, yeah, I think I need focus graph as their own thing too. And that's going to break some other modules, but we'll deal with it when we get there. Here, where we want is pointed. And would that just work? Well, we need non-empty. We need list. That's the internal list. And we need path. And path indeed is something we can try and get from non-empty. The path non-empty is actually not that simple. Sorry about that. Import that array as array. That sounds good. Maybe we'll take the constructor too and put them here. And we'll need edges. And we'll need edge. Do we just want to call it graph and we import it qualified? Ah, no, we can't. Yeah. Or we could call it pgraph, but tuple. And we continue down the list of things that are missing. Overlays. Okay. Overlays, vertex, edge, I believe. Okay, I think we're probably going to realistically need all of those. Edges we just got, and the rest sounds nice as long as we have pointed graph here. And then we need concat G, which is right there. And I'd be surprised if we wouldn't need fold G, but let's just get concat G for now. That's from data maybe. Wow, okay. That's premature. And yes, that's the regular graphs. And yeah, we need to change pointed graph pretty much everywhere. And here, yes, this overlay one just happens to overlay a regular graph, and that's fine. You can just import the regular graph like so. We need to non-empty. Maybe it's going to be a two-pointed here. Actually, pointed graphs just contain graphs now. So when we overlay, I think we don't need to convert to non-empty. I think we can just somehow overlay. Don't know how. Yeah, I need to think a bit about that. So we overlay a possibly empty graph with a pointed graph. First argument is gempty. Function returns the second argument. Otherwise, it's simply semantically the same as overlay. But overlay needs a pointed graph. Oh yeah, I just used two graph. Yeah. I suppose I just. Oh, I just realized something. This is not correct by construction. We can have several p vertices, can't we? Oh no, we can't actually. Huh. No, hold on. Oh wow, we can't. That's pretty cool. Huh. It's not obvious, but I think we can't. So can we do a two-pointed graph? And what's that mean? We can't convert all the vertices. So that's a little bit of a trick right there. We could extract an arbitrary vertex from graph and point it. And then what would it look like to seems like we need to fold. Can't just pattern match. And fold would be like what? Sorry. I'm a bit tired. It's getting late. Should 4G have a different semantic? Should this be... Yeah, because it should actually. It should have a semantic for a regular vertex and for a p vertex, I think. But are we going to need something better than, I think this is a catamorphism, right? Are we going to need like a histomorphism, I think is the thing where we keep the complete graph structure, or the complete original structure as well? Because we're going to need to call the graph 4G. So g.4g on the right hand side. Let's try and write it down. Yeah, I think I need an a to b, an added a to b right there, and this is going to be p, the point, and we apply p to that to p vertex, but we'll apply go 2x, but we'll apply fold g VO. Wow. Ooh. We need to deal with the empty case also. Yeah, because the rest of the graph can be empty. Or we ignore empty. Can we ignore it? This would be G fold G. And G fold G. as E. So we could pass some arbitrary B. But we need to pass something. We can't really ignore it. Yeah, I think we need to pass it too here. That's a bit heavy, but sounds like that's what we need. Okay. Okay, well, we might be missing things here. The graph comprising a single isolated vertex. Oh, yeah, well, we can't call this P vertex. I mean, we can't make, if we make a P vertex, no, that's fine. But it means that we can only call vertex from pointed graph once. And then we need to call vertex for the other side. Is that right? So G dot vertex for the other side, and then call P connect here, but then this needs to be a pointed graph and a graph to reach out a pointed graph. And that I think is fine. And then overlay is going to be P overlay, and it needs to be pointed graph to G dot graph pointed A. And therefore here, well, this is kind of moot. This is the same thing as P overlay here. So let's not have it. And here with fold, yes, here we need a pointed graph. And yes, I was maybe thinking to have a two pointed graph thing here, but probably not such a good idea. And concat G is not dealing with pointed graphs yet, so we probably need to do that. We'll need combine, I suppose, and then we know we want a pointed graph at the end, and probably well, do we want a non-empty? Yeah, we're going to need to have arbitrary decision about where we keep the pointing, and we probably so something's going to not work here. Yeah, concat G takes the combine, and combine being connect, it doesn't work because it needs to take a pointed graph and a graph. So unless we change this to take a pointed graph and a graph, we're in a bit of a pickle, but I think for now, let's just do that. Yeah, but that's just not going to work, is it? What does concat G look like for a regular graph? We don't have one. Okay. Takes a non-empty list of graphs. I think we said we pass it a non-empty list of pointed graphs. And I think that makes sense. So let's do that. However, connect taking pointed graph and a G graph, we might want, yeah, we might want actually the overlay one, and then what would we do? Yeah, we'd have to do a little bit of work, but I think, yeah, I think we need to recapture our overlay one here, and yeah, it shouldn't be called that. I mean, it shouldn't be, shouldn't have this particular documentation, but here, and so that would be P overlay, which is fine. But here, if we map two pointed graphs, then we're going to need to give arbitrary priority to the left-hand side graph, and we're going to say PQ, and it's going to be P to graph Q. So that's quite expensive. And it makes sense that we have to do that. Oof, my screen is jittering. Okay. I mean, I think that makes sense. And so then we have a connect one. That is that guy. And then the other one is just pconnect, connect PQ and pconnect P and to graph Q. And that should allow us to regularize this guy, two pointed, and then maybe it will work. Yeah, it looks like it does. And what are we missing now? Yeah. Yeah, connect one. It's going to be the faster way. And look at this. It compiles. We have path, we have circuit. We didn't have to change anything about it, but I mean, yeah, it's going to be, I think it means that the first thing in the non-empty list is going to be the point. So we just need to verify that with our tests. So let's do this. And that'll be the last thing we'll play with. So maybe before Comonad laws or what? I think we've made a change in module structure here. Oh, that apparently didn't break anything. Let's fix those. Good. And then, so what, Comonad laws? Hold on, do you mean you can test those? There we go. That's what I was expecting, and that's in algebra graph class. And our focus graph has moved to focused. And that's test, okay. So there was an error. And yes, so focused, and then pointed. And we don't have refocus on pointed quite yet. Might be repoint. And then we're missing a Comonad for graph. That sounds wrong. But here I'm supposed to be playing with pointed graph, and I'm going into any graph, so that's not right. I need to be saying that pointed is as p. Yeah, let's deal with the errors here. Any graph dot should all be any dot. Yep. And then good. Now we are now we want some pointed things, and they're called, well, let's call them p, not p. And so this is now, well, we're going to need an adjacency list thingy, which we don't have, but the rest should be p. Yes, we don't have that. So how's that going to work? Let's go to nonempty adjacency list, which uses to adjacency map, which uses 4G and AM, by the way. So, but I think that should be fine, actually. That will just work. And here we are. How's that? We need that pointed graph here. And we need pointed graph here. And that 4G will work as long as we import the adjacency map qualified, like so. But yes, 4G is mental here. So we are okay losing the pointing. So what does that mean? It means we use am.vertex as this, and then we look at graph, and what do we use? Probably am.empty. And so we might need to go back to using the regular adjacency map. We do use am.empty here, and we don't have an empty, oh, we do have an empty here for the non-empty adjacency map for some reason. Is that just a copy paste? It probably is just a copy paste. What's the meaning? Like, so we would be saying am_empty here. What does am_empty mean in this context? It means that it's just something that doesn't appear, and we kind of do need to know that. So let's just import regular adjacency map here. And then p.adjacency list is not a thing, but that's because we, oh no, I don't know why. It should be a thing now. P.adjacency list, maybe just a typo. No. No, it works. Okay, maybe it works. It compiles. Okay, Comonad laws failing. So extend extract. Oh, so it is extend extract, right? Extend extract to get equal ID. Not working. Okay, but that's good. I mean, it's good because we know we have we finally broke our test somehow, but it could be a number of things, right? It could be our adjacency transformations. That's a very good place to stop. So let's I didn't even do my usual housekeeping, so let's do it. Okay, copy and paste. In Graph Comonads, we have continued on Comonad for pointed graph, and next time we'll fix the failing tests for extend extract equals ID. Excellent. All right, so that's it for today. Thanks a lot for watching, and I'll see you probably on Saturday, maybe Sunday, for some resolution, making this Comonad instance for pointed graph work, and then playing a bit with the pointed graph, see what we think about it. See you later. Bye bye.